there is something in this shared task that they encourage you to actually look for discontinuous multiword expressions and try to actually capture them and detect them, even if there are tokens in between that do not form part of the multiword expression. Reflexive in languages like French, Spanish, etc. For example, se dérouler, which means to unfold. L'histoire se déroule, comme l'histoire se déroule, as the story unfolds, as the story is taking place. Se trouver, to be located, le pub, et se trouve à l'autre côté du campus. The pub is located on the other side of the campus, for example. Se passer, se battre, etc. You have a lot of those examples as well. And other potentially language-specific verbal multiword expressions. So the four types, so these two types are considered to be universal. These are considered to be, these three types are considered to be universal. These two semi-universal, and these ones to be language specific. Yes.
Is the other side of the coin? Is that a multi-word expression under the definition?
Yes.
Even though it doesn't have a verb in it.
Actually, you're right. I made a mistake there. I was probably just spending too much time last night trying to come up with the next one. That's correct. That is not a verbal multi-word expression, but it's a multi-word expression. So there are some examples here. Drink and drive, print and print, total drive from English. Anyway, the actual shared task. So there were 18 languages in total. English is not one of them for some reason. And out of these, 15 contain some sort of morphosyntactic information. Part-of-speech lemmas, so the data is lemmatized, and or dependency, syntactic dependency information. And we did not attempt the three languages that did not have any sort of morphosyntactic information, just because we thought that we wouldn't have very good results, and because we wanted to save a bit of time as well. But we should try them anyway. So the languages in green are the ones that we tried. So most of them. There were only 2 teams that tried this amount of languages. There was another team that also tried many. They actually did try all the languages. But most other teams they tried just 1 or 2 languages. So there were 2 tracks to the verbal multi-word expression shared task. The closed track, you are allowed only the provided data. So the data that the organizers provide you, that's the only thing that you can use. You cannot use something else. If you use an external corpus or something or vectors computed from an external corpus or whatever, or a lexicon or a lookup table, that qualifies as the open track. So they try to keep the 2 tracks separate. We were the only team that sort of attempted both tracks, and I now say why sort of. But basically nobody actually tried both tracks. And most people actually just attempted the closed track, actually. So the notation, you receive files that are annotated for the 5 classes that I mentioned before, and that's kind of like the class. But you're not required to categorize your extracted verbal multi-word expression. So you're just expected to say, this subsegment or segment of text is a multi-word a verbal multi-word expression or not. But you're not allowed, or you're not obliged or required to actually say, okay, this is an idiomatic expression or a lighter expression. A couple of teams did attempt to do it. Most didn't. We didn't. We just say, and the evaluation script that they gave you, it didn't look at that. So that's something to bear in mind. There were 2 types of evaluation. Something what the organizers called VMWE-based and token-based evaluation. So MWE-based means that if you detect the full multi-word expression, you get a point, a rounded point. You get one correct answer. If you got a partial answer, you get 0 points. You get that wrong. Token-based evaluation gives you partial credit for partial answers. Basically, that's what it is. So if you identify a 1-word from a 3-word multi-word expression, you get a few wrong partial credit. A third of one. There can be non-contiguous multi-word expressions. And every sentence in the corpus or in the data that is provided to you can have 0, 1, or more. And there could be embedded, so one multiple expression inside another, or they could be overlapped. So that's another tricky. We did not handle that case. We didn't care. It was just too complicated. For some languages, for example in Spanish, multiple expressions can become one. For example, encontrarse, which is the an infinitive form of saying cuenta. So it could be, you could find it in either form. It's the same verb, but conjugated differently, of course. And you can find it in either form, and you're expected to detect both, even if the first one is only one word. This is how the file looks like. This is what you get from the organizer. This is a phrase, a sentence, in French, so it's all at the sentence level. And here you can see an example of a reflexive, c'est passé. What you get. So and that's kind of like how they highlight it with an identifier, which is local to the sentence. The ID is local to the sentence. The tokens also have their own ID, which the IDs are also local to the sentence. And you get the category, basically, in this case, a reflexive. You also get a separate file which has the kernel U syntactic information. So kernel is another shared task about syntax and a few other shared tasks. And U is the universal, I think it comes from the universal dependencies, which another effort that Carla is Teresa, very, very involved in, so she can probably tell you more about it. But this is something, the format that you get. And basically you get the surface, the word surface of the sentence, you get the lemma, the lemmatized version of the surface, you get a couple of parts of speech. I think one is universal and the other one is specific to the language. You get all sorts of syntactic information which we did not use. You can see here that actually attempting to capture some multi-word expressions, even if you are actually capturing multi-word expressions yourself. And more interesting to us, there's also syntactic dependencies. So a syntactic dependency is basically this is a syntactic dependency. I don't know if you have done. It's another way of parsing. More commonly, people learn first constituency parsing tricks. This is an alternatively, I think, newer way of parsing, which is called dependency parsing. You have basically, you can see a sentence as a graph, and single direction graph. There's a lot of theory behind it. I think Carl knows much more about it. But the example that I wanted to say here is like an intuition that we exploited in this shared task is that if you see, for example, the other side of the coin, this is a sentence that contains the other side of the coin, you will see that all the words that have to do with other side of the coin are kind of linked together, and that coin, well, the root of the whole sentence is the verb is, but side is the root of the other side of the coin. So everything else comes from here. And I have a few other examples here, but I won't go into this in the sake of time. So what are you expected to provide back? You're expected to provide the same format as you got, but basically with your predicted labels, how you predicted everything. You have to give numeric IDs for the stuff that you find predicted. You are evaluated based on F-measure, and as I said before, MWE or token-based. So the intuition. We have two intuitions because we have basically two parts of our project, of our system. So we have part one and part two, let's call it. So the first intuition is that the expected output from this system expects it's similar to a tagging problem like in name entity recognition or part of speech tagging. So we said, what is the most popular method that is used nowadays for this type of thing? And it's actually conditional random fields. So that's why we use conditional random fields. So we use a sequence model, conditional random fields, CRF, to predict verbal multiple expressions. The second approach is that, well, the context of a word will be different. So the context of a multiple expression will be different in an idiomatic expression. Will be different when, as opposed to when the words are used on their own. For example, in the other side of the coin, the sentences or the context around that expression will be about any topic really, just that is contrasting ideas or situations. Whereas the word coin on its own, when it doesn't occur within the other side of the coin, could be about currency, numismatics, and other topics. So this is an intuition that is exploited a lot in words in the same situation. So we use something that we call the semantic re-ranker. So given a candidate multiple expression, we build word vectors for the full multiple expression and parts of the multiple expression, so individual words, and try to do pairwise comparisons using, for example, cosine to see how the degree or measure the degree of compositionality. And Martin and I did a paper actually we participated in another shared task on that a few years ago. So how do you marry the two approaches? How do you actually use the two together when you do that? Yes, we can, and actually Erwan did that actually. Position at the back. So what we did is that for the first approach already qualifies as a system for the closed trap. So we just did our job and for the first part and sent that immediately. For the second approach, the output will qualify for the open trap, and the reason is because the word vectors that we use were trained on an external corpus and on Europal. Why Europal? Because it had many languages, just because it was there, you know. But you can make an argument about using other corpus. You could use Wikipedia, for example, that has even more languages. It's bigger. So it was an arbitrary decision, really, practical decision. So, as I said, our best prediction, CRF prediction, was directly submitted as a closed track participation. And the CRF, you can ask CRF to give you not just the best prediction, but a number of predictions, say the top 10 predictions, or the top 100 if you want. When we say, well, let's look at just the top 10 predictions. And we apply our word vector approach to re-rank these predictions, you know, to see if we can improve on this ranking, and then we would submit this as our open track participation. However, we didn't have time, we didn't finish. Yes?
A question, please. So how did you ask the CRF to predict the 10 best candidate?
It's a parameter in the prediction program. There is a parameter, you can tell it n equals 10 or whatever.
So you changed the parameter setting in the CRF++?
Yes, in CRF++, yes.
So you download the source code instead of the compared one?
Sorry?
So you run the source code of the CRF there?
No, it's a parameter in the command line.
Okay.
Yes, but I'll show you later, it's very simple. It's not that difficult. I just rerun the whole thing, basically, with that parameter. So we didn't have time it was very short the period that we had. Anyway, so so we use CRF++, that's the web address for that tool. So it's a tool that you can use. You can specify your own feature sets, and you can go away and do whatever you want. You know, with it. So we also we merged the two files, the kernel U and the PARSEME TSV file. TSV stands for tab separated value file, because they're tab separated value files. And we designed CRF++ feature templates. Basically, that's what features you want to use. And I'm going to talk about exactly what features that we used actually. Then we conducted 5-fold cross-validation experiments on the training set, because you're only given the training set. It's an annotated training set. So we did 5-fold cross-validation to basically using all the templates that we developed to select the best template. And we used the best performing template per language to train on the full training set and predict on the blind test. Because the organizers give you a blind test without answers. And you are required to provide the answers to that within your system, send them, upload them to a website, and then they do the evaluation themselves. That's how it works. And that's what we submit to the close. So what's conditional random fields? I'm going to talk quite briefly, but basically it's a discriminative probabilistic sequence model as opposed to generative. I don't really have time to go into the details, but I'll explain with a name entity recognition example. Imagine that you're getting input and you want to decide whether each token, each word in your input is nothing or is an entity, either a person or a location. Person or location. And we have this sentence, Jack London went to Paris. So obviously, any decent person would know that or deduce that London is a surname. So London is a person token. It's not a location token, despite the fact that there is a city called London. So this is our what we call an observed sequence, a sequence of tokens, a sequence of words that we get. And then we can flag everything as nothing, everything as person, or everything as location. Or combinations. So those dotted lines are kind of like transitions between labels that we can take to go from token to token. As we move from left to right, we go from, for example, Jack, from person to another location or person, etc. This is what it's called the state sequence, or the sequence of states, or the sequence of labels. And this has a lot to do with like state machines and other formalisms. So a not very good name entity recognizer system would go Jack is a person, yeah, Jack is a name, popular personal name. London, it's a city, location, and then you go went, it's not an entity. Two is not an entity. Paris, it's a city, it's a location. But obviously this is wrong. The correct would be person, nothing, location. That's what you would do. What you're expecting, so you have two candidates. You have two candidate state sequences or label sequences. And what you're hoping for is that the state sequence or the label sequence, person, nothing, location, is more probable, according to your model, than person, location, nothing, location. That's what you want to find, and that's what you do. Now, strictly speaking, what I'm describing here is actually a bigram model, in which the current token depends only on the current token state depends on the previous token label or state. And you probably have seen this type of diagrams, and this would be how it would be realized. So basically, this is also what you would also do in a generative model. You're actually assuming that somebody came up with these locations or this sequence of states, and they uttered this particular sequence of tokens, and your job is to basically decode that. It is actually called decoding, the job that we're doing. So this is what you can do with a bigram model. But you can also do it with a conditional random field. But conditional random fields allow you to encode more exotic dependencies while retaining tractability. So it's a very powerful tool. Now, in our specific case, we have access to all of these and more features. Word surface, the surface of the head for the current token. So as you will see that we have a lot of head, basically the head of the current token. That we exploit that information through the dependencies. And the dependency relationship between the current token and its head. So that's what we try to do. Oops, sorry. And with that, this is one of the templates that we use, that we developed. And it looks like an octopus. So if you compare it with this very simple linear sequence, that's what you can do with a relatively basic model. And with CRF, you can go crazy and do that, and you will finish. And if you try to do this, you can do it with language models or HMMs or other type of models. But your problem will become untractable. You won't be able to do that. Now, the original part of this, or what we found that worked best, was the features on top here. the head lemma for the current token and the dependency relation. The head, the part of speech of the head and the dependency relationship, the part of speech of the current token and the dependency relation with its head, and so on. These other features are very common in name entity recognition. We just copied them. So we just thought it was kind of like a baseline. So the original part here is this, the things at the head of the octopus. Now, so that's the first approach. Now the second approach, so the semantic revamping, how does that work? So as I told you, we use EuroPAR, a very, very big corpus, which is basically the proceedings of the European Union Parliament translated into, I don't know how many, all of the, or many of the official languages of the EU. It's not available, unfortunately, for Farsi, Maltese, or Turkish, so we did not work in these languages for this part of the system. Erwan developed code to build word expressions from candidate multi-word expressions in each of the top 10 CRF-predicted sequences. So for each of the predictions that the CRF system is giving you, we give it to this system to give us to try to re-rank it, and we produce one vector per sequence. So you have we produce a lot of little vectors per multi-word expression, but for the whole sequence we combine them in a very weird way. Well, we had very little time to do this, but so a lot of it was just kind of like, okay, let's get it done. But it works actually. It works very nicely. It works very nicely, folks. And but basically, we try to represent the whole sequence. We actually represent the whole sequence with one vector, so that we can then compare against sequences. Sorry. So we use the comparison, or the way is that each of the sequence vectors, we do our decision tree regression using Vogel. And that, so basically, if we look at the gold standard label, and during training, we look at the gold standard label, and if we see this is the correct answer, we give it a value of 1. The sequence corresponds to the gold standard, we give it a value of 1. If it doesn't correspond to the gold standard, we give it a value of 0. And we use the regression so that we could then rank later on. Oh yeah, this is what I was saying. A regression produces a score between 0 and 1 per predicted sequence, and we use that here to remember. So this is an actual example. I hope you can actually read it. The most important bit, so it is a sentence again in French, mostly because French is the language of one of the languages that was ready first. I sort of know a little bit of it, so I was able to work in it. So I just kept working in French. So this is the sentence. These are the features that we're using, combining that octopus, as we saw. And this is the gold standard. So the annotators told us that there is, this is the beginning of multi-word expression, and these are intermediate tokens. And the multi-word expression is prendre le dessus, which means, what did it mean?
The upper hand.
The upper hand. Yeah, have the upper hand. Anyway, these things, then the gray area, the gray boxes there, are the 10 best predictions by our system. So this is what you get from our CRF system. And the first prediction, or like the top prediction, is actually incorrect in the sense that it does not predict the gold standard. The correct prediction is actually number 3. So this is incorrect. It would be flagged. It's incorrect in our attempt. So what we do is that we look, for example, we look at that, right? So this would be the correct answer. So how do we attempt this? So we build word expressions for. So this process is repeated on every sequence. So because we need to know, we want to find out which is the correct sequence. So imagine that we're actually working on sequence 3, the correct sequence. We build a word vector from EuroPAR for the full multi-word expression. We also compute word vectors using the same corpus for its individual words, for prendre, le, and dessus. We also compute for word vectors using the whole multi-word expression minus one word. So, prendre le dessus, apprendre dessus. And we also build word vectors for the other sequence, the multi-word expression as detected as flagged in the other sequences. So that's why it has W2, W4, W5, W6, because they come from the other sequences. So W3 means that it comes from the third sequence, W2 comes from the second sequence. You can see that dessus is the only word, it only has an I there, an I here. So it's a single one. Anyway, we compute similarity scores. That's what that same means. We compare similarity scores, and you have a choice of using cosine with IDF, inverse document frequency cosine without the IDF, so raw cosine, Jacquard, mean max similarity, and that's it. But basically, you have the option of using that, and then we summarize. So this produces a lot of scores. But we want to find basically one vector of one of the same length. So we produce this. We summarize them using mean. Basically, we average the scores, take the mean, take the max, and that's actually what makes it into the final feature set, feature vector for the sequence. Now, did it actually work? So. Actually, thanks for Erwan for finding this last night. It's actually very good. So I was thinking, well, actually, for this sentence, would our algorithm work? Would our re-ranker actually work? So here you can see, on the top, in this line, you have the probabilities from the CRF model, and they are sorted in a descendant manner, right? So the first one is the most probable, and then slightly less probable, until you get the least probable at the end. And SEM is the result. This is a result of the regression model, basically, from after computing over vector doing the cosine thing and doing the regression. This is what you get. And yes, if you actually resort by SEM, you get a 0.5. Score of sorts, and that is the way the system, our system, would re-rank the CRF prediction. So it would, in this case, it would work. Now, how did we do? So I'm not expecting you to read this. This is a bit crazy, but this is the results of other systems for every language in the whole competition. The ones highlighted in red or circled in red is our system performance for the CRF only. Remember, we did not have the time to submit the re-ranker, unfortunately. But even with the CRF, you can see that we kind of get a good ranking there. So we are either second, usually second. There's a couple of first, a few or like 4th or 5th places, but it's mostly. Although you need to take this a bit with a pinch of salt because, for example, for Farsi, we were the second one, but also the last because only 2 systems participated in Farsi. So, anyway. Now, comparing the actual CRF with semantic re-ranking. So, how much have we improved? So, this is a comparison in the overall system. So, the first column, CRF, is the F1 score for the CRF, what we submitted to our official CRF submission. SEM would be the semantic re-ranker. And in many cases, it improves the result. Sometimes it kind of stays, but overall, it kind of improves. That's not a big jump. So, this is like there's a few improvements there. If you go across the empty boxes there is Farsi, Maltese, and Turkish, which there was no Europower data for them, so we didn't do anything with them. Now, another thing that I observed was that there was which is this last column called PS. I thought I was thinking, well, I was wondering how many of the multiple expressions that are present in the test set were previously present in the training set. That is, you would expect that if your system has already seen a particular multiple expression, that it would perform better, right? As opposed if it's a completely new. So it was trained, let's say, it was trained with Europarl data from 2005, let's say, this from 2005. What if it finds swipe left or swipe right? It wouldn't find it, right? So I was wondering, well, how many are there that are already seen? How many are new? How many are old? So I computed this percentage. So PS means previously seen. This is the percentage of multiple expressions total, as in total frequency, including repeats, within the test set. The percentage of previously seen multiple expressions, the percentage of multiple expressions in the test set that were already present in the training set. And this is what I found. For Czech, there was 92%. That's a lot. Other languages, German, 39, almost 40%, and so on and so forth. So it varies a lot. Some languages, they have a lot. Some languages have a little. And something I observe is that if we have a lot, our system tends to do well. If as a little, like a modest increase, our system doesn't do very well. I was like, wow, so obviously it is helping our system. But another thing I was thinking is like, well, what if you think about it, you could actually build a very basic system, a very simple system that just looks at the multiple expression in the training data, does absolutely no NLP, absolutely nothing, and just tries to match as best as it can those multiple expressions from the training data in the test data, in the test data. And basically, this percentage there would correspond to the recode score that you would get if you did that. And if you are very clever, you could probably build your system in such a way that you achieve a 100% precision. So I was thinking, what would happen if you actually achieve 100% precision, as meaning that of everything that you found, that you flag as multiple expression, really is a multiple expression. And this is the F1 score that you would get for such a simple lookup system. And the scores are very high. And I said, oh, wait a minute. So this hypothetical lookup system that has nothing to do with NLP would perform very well, obviously, in languages where there's a high recall or a high percentage. And I was saying, how would you compare against the rest of the systems in the competitions? And here's the answer. This is the number of languages that each system ranked at different places. So the PS is the previously seen baseline, you could call it a baseline. This is this is one of the transition, one of the systems. Same as our system. Mum, I don't know, it was called like that. The first three characters from each system. CRF is our other system, the one we submitted. And you can see that previously seen if you had submitted that system to the competition, that baseline system to the competition, which would actually qualify as a closed system, closed track system, would achieve first place in 13 languages, 6th place in 2 languages. That's very good performance for something so simple. The other system, the system that beats us most of the time, they would still get quite a very good performance, so they actually did something very good. Unfortunately, they haven't published the paper. I've been looking every day to see what actually did. They haven't done it, so I probably won't know until after Valencia, and we can talk after that, I can tell you. But our system would, the semantic system would actually do very well and would actually do better than most systems. So another thing is that it's saying, well, how much is each this fact that there's a lot of variation of previously seen data, previously seen multiple expression, how much is helping the other systems in the competition. Can I actually find out? Yes, you can, because the results are public. And this is what I found. The colors are a bit weird because there's many systems, many languages. But basically, what you see is that this is the F1 score. Oh, sorry, no, the other screen. This is the F1 score. The y-axis is the F1 score for all systems in the official ranking table. And PS is the percentage of previously seen multiple expressions. And you can see there is a positive relationship between the two. And in fact, the Pearson correlation coefficient is 0.63%, which is positively correlated. It's a quite strong correlation. Something that you will see is that here the colors correspond to the language, and funnily enough, all the colors sort of cluster together. Look, the purple here, lighter purple here, blue here, another purple here, yellow here. So basically, what it means is that if you're doing bad, doesn't matter. The rest of the systems are also doing bad. If you're doing good, other systems are doing good. And yes, the previously seen, or the fact that there are previously seen multiple expressions in the dataset is helping everybody. So not only us, everybody. So that's something to consider. So conclusions. We develop a system based on conditional random fields that exploits syntactic dependency features. And it performed very competitively at identifying verbal multiple expressions. We can also re-rank those predictions, the top 10 predictions from CRF, using semantic vector regression, achieving very good results, so improving our performance in most cases, not all cases, but in most cases. And most systems tend to perform well if there's a whole proportion of previously seen multiple expressions in the test set. So that's something we found. And is that important? Is that a good thing or a bad thing? Well, I really think it depends. What is the reason you are defining multiple expressions? Why are we doing this? This really was an academic exercise. This is like, let's go and have a go at just identifying verbal multiple expressions in as many languages as we can, and see how much we get. It in itself is a very good effort. I think it's the effort that has compared this amount of languages from so many distant family language families. So from very different, very diverse language families. So it is a very good effort. But really, at the end of the day, you're doing this because you have a purpose. There's a reason why you're doing this. For example, you may want to use a formation translation. You want to make Google Translate to translate kick the bucket using an idiom in your target language or in another target language, and you want to use that. So in this case, if you're doing machine translation, it's probably good to have a good performance in multiple expression, in previously seen multiple expressions. So I don't care really if I'm training on previously seen multiple expression. That's okay, that's all right. But if I'm working on lexicography, if I work in the English to Irish dictionary, I don't really want to see previously seen multiple expressions. Why do you want to show me things I already know? I want to identify new things that people are saying now, that the young people are saying, the new stuff that are coming out in the social media. That's what they want to capture. Not necessarily what it's all. What it's all is presumably already in a dictionary. So the stuff that is in the dictionary, I don't want to find it again, unless I want to confirm, confirm what I already know. But if I want to define new things, I want to focus on previously seen. Is F1 the best way of evaluating this shared task? Well, again, it depends. If you are, again, in the lexicographic example, perhaps recall is more important. Recall is more about coverage. How many of the stuff that is there, of the multiple expressions that are there to be discovered, what is the percentage of multiple expressions that you actually discover? That's recall. Even at the expense of having bad precision. Why? Because bad precision really translate, good recall and bad precision translates into having a lot of false positives. So the only thing that you're doing is that you're giving more manual work to the lexicographers. They have to go through all this candidate list, and they have to basically sit there and say, no, this is bad, this is bad. Of course, precision would be nice to have, but recall would be presumably more important than precision. If you're building a computer-aided language learning tool, you probably, and for example, an exercise in which, or you would just want to show an example, a good example of the usage of a multiword expression. You want that example to be correct. So perhaps you're interested more in precision than recall. You don't want to find all the examples that have that multiword expression. You just want one or two, but very good ones. So for future work, what do we want to do next in our future work? So we would like to participate in future iterations of this shared task, and we would like to recommend the shared task organizers to develop application-oriented verbal multiword expression tasks with more appropriate evaluation schemes, more for the actual multiword, like what do you want to do? Like, even if it's a simulated exercise, but what is the purpose of doing this? Why are we doing this? What is the intended application? And then try to come up with what are the appropriate evaluation metrics for that application. That's what we're going to do. Just one would be a few that I would be interested in trying out myself. As opposed to our first approach, the CRF approach, well, I don't know if some criticism that I would have around my own work is that I look at the sequence of tokens as a linear sequence of tokens. Jack, London, Web to Paris, one after another. But you could make the case that you could make the case that, well, that you already have the dependency tree structure. Why don't you just navigate it? Do a tree-based CRF system, and there are some applications, there are some tools already developed for that. So basically, we want to explore tree-based CRF systems as opposed to linear sequences. Semantic vectors, we require more analysis. For example, we haven't done much analysis as the percentage of corrected errors versus the percentage of introduced errors, but we did do a little bit on that anyway. And we can probably evolve more into discussion. There's other type of semantic vectors. Word embeddings, for example, is very popular nowadays. We can try them as well. There's non-negative matrix factorization. There is LSA, latent semantic analysis, which is a bit older, but we didn't even try those things because we didn't have time. But there's a lot that we can explore there. And also, we try re-ranking. There's no need we have to stop at re-ranking. We could perhaps integrate those semantic vectors as features for the CRF system itself. So instead of having like a two-pass system or a two-step pipeline to integrate everything in one system. And that's it. That's all I have for you. If you have some questions. Yes.
Can you go back to the conversion slide?
Yeah.
So the top one where you say the syntactic dependency feature is very useful. Some of the tree banks had information about multi-word expressions and others didn't. Did you notice a significant difference between which ones had and which didn't?
No, we didn't look into that.
Okay.
We didn't. So that was in the columns in the middle. I did notice they have that, but we didn't work with it mostly because so the shared task really the shared task started at the end of December and finished at the beginning of February. And we really only started after Christmas. So we started like the second week of January or first week of January. So we worked very fast, And so we just went with whatever we felt would work. Again, this is not a very good answer, but those would be one of the things that we would like to look into, for example. We are provided this information, and we didn't look at it.
Yeah.
We didn't even look at it.
And not only the morphological features, but some of the tree banks in their dependency labels, they've actually annotated multi-word expression in the labels. So
I did notice it for French, but we didn't look into it.
Yeah, because in the Irish tree bank we haven't labeled multi-word expression yet, but it would be interesting to know how easy it would be to find them anyway, just based on the dependency attachments that we have. But we can talk about that offline.
Yes.
Sorry, what's the question again?
Sorry?
What's the question again? The question about.
The question was that in the feature set, the kernel used said for some languages there is already multi-word expressions identified there, and basically did we use it or did we notice that there was a performance increase from those languages? But we didn't use it, and we didn't do an analysis on which languages used it or not.
Yeah, there was a team, right? They use the official data because they think, oh, there are so much syntax information, and that team, they trained their parser based on the official data. So they didn't use the outside data, and they use offer the data and train the dependency parser and do the tagging.
Okay.
Yeah, from another university.
Was it the assistant participating in the shared task?
Yeah, it's in the closed track. But in the beginning, the organizer classified them into open track because they think, oh, this team uses the parser, so they classify into the open track. But later they found, actually their parser was only trained on the training data. They didn't use any other data. So they later moved from the open track to the closed track.
I didn't know.
No.
Any more questions?
Yeah, I was wondering whether, linguistically, what you took away from it, like what characterizes multi-word expressions very well, because it seems that most systems, if I understand correctly, like they still really rely on the training data, so having some kind of sample of this. And so do you think it's like it's mostly contextual? Because to me it feels like it's, especially like for new multi-word expressions, that it would increase the frequency of the other words occurring, overall anyway. So a multi-word expression makes a particular word.
You mean the type of feature if frequency would help?
Or like the way that, for example, like in neologism, so the stuff that Martin was doing with probably still doing it with the words become more frequent because now has a new meaning. So my thinking was that if you have a multi-word expression, a new one, and you have a particular word that features in this expression, then it's make it more frequent.
Yes, potentially would make it more frequent, but there are words that are usually only used in multi-word expressions. Anyway, but we kind of use a similar intuition in the semantic re-ranker, basically, but we look at basically we think that there is this thing called frequency ratios. That if you divide so for example, the other side of the coin, you will probably, on an AV corpus, you could perhaps expect to see the word coin occurring in general, with and without, inside or outside that multi-word expression, more times than the multi-word expression.
Well, it would probably depend on the word itself, no?
Well, it will never appear, the multi-word expression, the other side of the coin will never appear more times than coin.
Well, you think that's true for...
It will only appear as many times.
No, I get that, but say if you look at other contexts where it wouldn't be a multi-word expression.
So that's kind of like the intuition that we exploited in the word vector, the word vector thing. So when we build, let me try to go back to it. When we build these, for example, these unigram word vectors as opposed to these ones, we would expect, or intuition is that the context of this word vector would be different to this. So there would be some overlap. But points can occur with a lot of many other words, that have nothing to do with Dessus, for example. So we assume that if this is a valid multi-word expression, that the similarity score between the two would be low. Yeah. I don't know if this answers your question.
I think it was maybe too many questions in one, but I think so you think this would characterize multi-word expression that's basically to get at the difference between multi-word expressions and something that was syntactically similar.
Well, I don't. Well, whether this can. You mean is this is the best way of?
Yeah. Well, I don't know if actually there are. At the beginning, we had doubts about whether, because for idiomatic expression they are supposed to be non-compositional, so it's easier to know what we expect in terms of when you compare different parts of the expression against the expression itself. So that's the case where yes, you expect a low similarity and not. Well, anyway, so the thing is, which direction. Actually, when we did the problem is some of these multi-word expressions, they are actually compositional. Some of them very compositional. So at this stage, I don't think we can really. Well, I'm at least I can't completely answer the question in the sense that what the classifier makes of these similarity scores, we don't know exactly actually.
Now, well, that's kind of like your job as a researcher to find out which is the best way of exploiting the intuition. It doesn't mean that this is the best way of doing it. Like that's why research in this area has continued. That people are coming up with new things. They exploit different. Like if you go to the early 90s, you will find things like mutual information. Log likelihood scores like that, and they're very useful, but they have some limitation. Actually, you could use those things here as well, as features of the multi-word expressions. I did that in my PhD, and I was getting very good results. But like whether that is the best way of doing it, maybe not. Maybe it's one of those cases that it works for some cases, but not others. It's basically, I do think, but I do think that there's a value of having like a linguistic intuition of what you want to, of how you want to proceed, and then like in your mind it makes a lot of sense. Oh yeah, it must be true, yeah, and you probably can come up with numbers to back up your idea, but then it becomes tricky how you actually operationalize that. How you actually write an actual program that exploits the intuition. So I think it's that.
Oh yeah, no, it's fine. I was wondering the same
way. Yes.
Yeah. You back to the score again. The table of many languages. Do you remember? You list the table. No. Yeah, this one. So I found one interesting part. So in most languages, if we use the exact match, not any technologies, then the score will be the precision score is 100, and the record score is also high, right? But for Polish, there is a swap, right? There is a difference. So the CRF is 67. And the PIs is 66, right?
Yes, yeah.
But for all other languages, it is the PIs is actually higher than the CRF.
Not all the time, no.
Well, should be answered by this graph. So these are all the scores.
Yeah.
So yeah, for example, here you get, this is 25 and you get an F1 score of 50. Oh, well, sorry, these are recalled. This would be recalled, so that's not a, sorry, this is not a, I should produce another graph, which would contain the F1.
But even on this graph, you can still see that you have values under the diagonal, so it means that you have cases where the CRF score is better, well, the F1 score for CRF is better than the proportion of previous 15 sentences.
There are cases. There are many cases of that, though. But overall, they tend to